Okay, so what I planned is coming few weeks. I'll be probably make couple of videos for you in different topics. Now it should not be it's a class wise, but rather I pick up couple of topics and make videos on that. So what we can do is once you receive the videos, you can go through, and if you have any queries or any points that need more discussions, let me know so that I'll just try to clarify things again. So today we'll be talking about doping and surface modification. Now, so far we have covered several things in this class. Mainly focusing on the growth of thin films and their characterization. And thin films is very important, but the things that we have discussed covers that how you can grow thin films, uh, but how to exploit these thin films for the fabrication of devices uh, is critical, because when you grow it, you grow all over the substrate or over the wafer. But now the thing is that how do you make use of these thin films for fabrication of device? Remember, the device size is extremely small, so we'll be concentrating is very small part of the substrate and the thin films. Now today what I'm be discussing is doping and surface modification. This is very important part for thin film based technology development. Doping means like you take a materials and change their electrical property by introduce other materials, selective materials. Sometimes you also need to make the surface property change. So these two topics I'll try to cover. Again, I start with the reference. Now, since we'll not, meet each other at the moment, I will mostly be following a specific book such that you have less trouble of finding references. So, as I earlier mentioned, also that this is the book that is going to be used mostly, and in this case, the chapter 5. Okay, so look at the chapter 5, and most of the contents you'll get, a little bit here and there. Some slides may not be from there. Now, let's start with the doping processes. So there are several processes for doping and surface modification. Now, I'll be mainly, focusing on the silicon. Okay, and the silicon is a materials mostly used for microelectronic technology development. So silicon is one of them. I mean, it's not limited to silicon. It can be anything that you can think of, any materials, any surface you can think of. But silicon could be one of them, which is mostly used for the technology development. Right? Diffusion and ion implantation. So these are the two processes for doping. The first one is diffusion, and second one is the ion implantation. So both the topics I'm going to cover. Diffusion I have already discussed earlier. What do you mean by diffusion? When we discussed about growth of thin films, because in the thin film growth process, diffusion takes a very important role to decide what kinds of surface structures that forms, right? So in this case also, when you dope, so you introduce a doping material into the film or into the substrate, and let these atoms that you introduce diffuse inside the material and settle is specific structure. So yes, there is another process is called oxidation, and oxidation also is important techniques, very often used, mainly to form the silicon dioxide. Silicon dioxide is a dielectric material. It's an insulator. It's a dielectric materials, and dielectric materials are very important for various purposes, particularly when you talk about thin film transistor. You have gate dielectric, and if you can make a part of silicon substrate into silicon dioxide, then you have basically grown gate dielectric materials on the substrate itself. So that is also another important process that's important and are being used for thin film based technology. Yes, so that's the dielectric material. Now let us move that basically the importance of doping and surface modification. Now in this corner what you see is silicon wafer. So they are silicon wafer cut from a pieces, big silicon material, bulk silicon rod, and I have discussed about this, that how things are done, how do you cut the silicon wafer, right? And then so this is essentially our single crystal in nature. What is important is when you talk about technology development, uh, mostly for electronic devices, electrical conductivity of the material is the things that we exploit in the device. Right? So, what is important for electrical conductivity of the solid? So, essentially, it's like charge transport through a solid material, which is guided by the energy band diagram of the material. Now, this I have discussed also. Energy band diagram for any material. Now, the material can be insulator, right? As I mentioned here, can be conductor and can be semiconductor, right? And you know why they are so. So this is showing the band diagram. Now, for the insulator, you have a energy gap. So you have valence band, you have conduction band. Now, for insulator, you have a big energy gap between valence band and conduction band. Whereas in the case of conductors, this valence band and conduction band actually overlap and there is no gap. However, for semiconductor, it is like insulator, but the gap is little bit lower and of the order of few electron volt, like 2 to 3 electron volt. Whereas in case of insulator, the same gap is over 3 electron volt. Now, what you see in this side is the distribution of electrons. Right? So, what does that means? That means is when you calculate band structure, so you have valence band and you have conduction band, and so these are band in a sense that all these energy levels are packed in a very small energy interval. Now this you know that they are not continuous band, so they're still discrete in nature, and filling up these energy levels is again followed by the Pauli's exclusive principle. Now, when you calculate energy band diagram for a particular solid, uh, then you calculate the energy levels first from the potential utilizing the Schrodinger equation. Now, whether those energy levels will be filled by the electron or not, that is decided by Fermi function, which I have discussed in details earlier. And in this case, whether these states will be filled by the electron is decided by the Fermi function and the number of electrons that you have. So how this valence band is filled by the electron, that is basically represented by the electron distribution. So you'll have, for insulator, you see the electrons are staying in valence band. Of course, in case of conductor, you have all the energy levels in the valence bands are filled by electron, and you have some electrons, some part of this electron distribution in the conduction band, and these are the free electrons which take part in charge transfer or current flow. Now, if you look at the semiconductor, then of course, again here you see that since the gap is small, uh, you have electron in the valence band and some electrons in the conduction band as well. And these electrons are basically, take part in charge transfer. Okay. Now, if you look at the silicon atomic structure. So the silicon is a 4 valence electron. So silicon has 4 nearest neighbor, and they share electrons from each of these 4 nearest neighbor to make outermost orbitals, electron orbitals filled by 8 electrons. So that's how that we know. Now what is happening here is that if you take this material and calculate the energy band diagram. So you have valence band and you have conduction band. So this Eg is the energy gap, and Eg is something like, for silicon it's 1.1 electron volt. Now how these energy levels are distributed, so this is not uniformly distributed, but you have some sort of distribution which is essentially represented by n into nc, which is function of energy. So you have NV, so C basically for conduction band and V for valence band, right? So that is the distribution. Now whether, of course, you have uh, these states are filled by the electron or not, that is of course decided by the Fermi function, which I already discussed. And the Fermi function is, of course, depends on the temperature. So if you remember earlier what we discussed, that if you plot here in E, so let us put another axis and put here Fermi function, right? So this is f of E. So see, I am writing are not very good, so I'm trying to manage. So this is your f of E, and if you plot the f of E, then essentially, let's say t is equal to 0. T is equal to 0. So T is equal to 0. Kelvin. So you'll have and your Fermi energy at the middle. So essentially, you have a kind of step function, right? You kind of step function here. So this value is 1, right? And here is 0. So all the levels. So you see the function is 1. So this part, is filled by the electron. This part is filled because function is 1. So you multiply f into Ne. So that basically gives you the area, and this is filled by electron. Now if you increase the T, let's say it's greater than 0, right? T is greater than 0, then all you have as sort of like, so this is halfway, so it should be something like this, and then keep increasing temperature. So at some point you will get a function something like that. Okay. So what is important in this case is that the tail of this Fermi function actually enter into your conduction band. So that means if you consider this part, this area, so some of the electrons are essentially there in the conduction band, and that is how you see in the earlier slide that semiconductor has some of the electrons right here in the conduction band, and they take part into the charge transfer. Now, so why this part? So as I said to you that you increase the temperature, and if you increase the temperature, so this one is kVt, that's the energy, and T, if you take T is something like 300 Kelvin, right? Room temperature, 300. This is 300 Kelvin. So if you take 300 Kelvin, then something like you have energy. If you convert that energy into energy, it will be around 25 milli electron volt, right? And in 25 milli electron volt you supply to this material, and this energy, what happens is breaks one of this bond, covalent bond, and it release electron and left a hole, right? So that is what so these electrons are actually pushed to here. So essentially you have now hole here, right? You generate some of the electrons from here and push them there. So these are all electrons, right? So these are all electrons, and these are all hole, right? So this is how actually you generate electron hole, and you pump some of the electrons to the conduction band, and that make the silicon as some sort of conductor. So typically this happens even in the room temperature, and consider the resistivity for intrinsic silicon. So intrinsic silicon is, there is no doping in the pure silicon material, is some sort of like 2.3 into 10 to the power 5 ohm centimeter, and so this is some the resistivity, some sort of resistivity. But if you look at even if you compare this resistivity with the conductor like copper, which is 1.7 to the minus 6 so ohm centimeter, so it's extremely low resistivity compared to silicon, but still in the room temperature you get some sort of conductivity for silicon, which is of course not the case for case in case of insulator, because this gap is really high, and then this still really doesn't reach to the conduction band. You cannot pump electron into the conduction band for this. Now, when you talk about doping, now this use in these slides, you see some part of periodic table. So what you see in this case, these are all semiconductor, right? Like silicon, germanium, of course. Carbon is different. Carbon also can be used like in different form. They can become conductor, like graphene, like graphite, right? So yes, now what is important? So this is a 4 valence element in periodic table, and in this is 3 valence electron atoms, and this one is 5 valence electron atoms, right? So what you see that this atoms like boron, aluminum, gallium, indium, so they are basically are used as a dopant for p-type material. Now since they are 3 valence electrons, so you know that in case of 3 valence electron in the outermost cell you have basically 3 electron, 1 electron less, so that considered as a empty hole. So if you dope with this, so you give extra hole into the material. Similarly, in case of these atoms like phosphorus, arsenic, and antimony, So they are basically used as an N-type dopant for silicon and germanium. Uh, Nitrogen and phosphorus also used for N-type dopant for carbon. Okay, carbon element. Now, this boron, aluminum, gallium, indium is p-type dopant for silicon. Aluminum, gallium, indium normally are used for p-type dopant for germanium. Right, so this sort of tells you that what are the elements what are the elements you need to do to get what type of a specific type of semiconductor, like either p type or n type, and with which elements you're going to which material you're going to do. Okay, now for I talked about intrinsic conductivity, and then you know some of the elements which you need to do. Now here I again repeat that 5 valence uh, electron atoms, which are essentially these atoms like arsenic, antimony, phosphorus, are used for N-type, and for silicon, germanium, aluminum, gallium, indium. So these are used for P-type doping. And what you do in case of doping, so you basically replace one of the silicon atom and introduce either 3 valence or 4 valence, 5 valence atom. When you give 5 valence atom, so 4 of the outermost electrons share by 4 nearest silicon atoms, but you have one unpaired electron. So that is sort of like an extra electron you provide into the system. Similarly, in case of boron or 3 valence electron atom, so you have 3 electrons present for boron in the outermost shell are shared with 3 silicon nearest atoms, but in one, since it has one less electron, so it introduces one hole into the material. So this will be a p-type material, this will be an n-type material, right? Now what happens here? So when you actually dope, now look at the electronic structure, energy band diagram of an atom for n-type material. So when you dope, if you introduce an extra atom into the system for 5 valence atom, and that every extra atoms that you introduce in the lattice, so it's introduce one extra electron, and these are all localized electron. Excuse me. So essentially what you have, you introduce an extra energy levels, and this energy levels contains all these extra electrons. So now you remember, even if it is drawn a straight line like this, but this is essentially discrete energy levels in the same energy, and they are all localized state. So this is called donor impurity energy level, which will be close to conduction band because you add electrons. So these electrons are close to conduction band, and it can actually go very easily here and will be available for charge transfer. Okay. Similarly, in the case for p-type material, because you have holes, so you introduce the free states or hole state close to valence band, and in this electron can they can take part in the charge transfer. Okay, so this electron can come and fill these states. So that is what the changes that you made when you dope a particular material with to make it either p-type or n-type. Now, in this case, now let us concentrate that how do we basically dope a particular material. Now there can be different techniques. Now let's start with the diffusion techniques. As I said, that the diffusion process are very important for doping. What you do in this case is that this dopant gas. So there is a two-step dopant diffusion process. The first step what you do is you have to make a silicon dioxide mask. So which means that you now restrict the area of the silicon substrate on which you want to do. You don't want to do all over the substrate, maybe very specific part of this substrate to either N type or P type, which what is normally is done for case of device like PN diode. Some part is P type, some part is N type material, right? So what you do is that you take a silicon dioxide mask, so you cover up, and then you deposit this dopant gas in on the area where you want to do. So this will be a area that you deposited some dopant gas. Now this second stage, what you do is you have to heat it. It's after you deposit this dopant atoms, you heat it something like 800 to 1000 degrees centigrade. Now when you heat them, so these atoms that you have deposited, uh, they diffuse on the silicon, right? Now when you grow it like you grow like it's a random deposition of the atoms. Now these atoms diffuse into the silicon and replace the silicon atoms from their crystalline position and sits there. Right? So that is what is done. Now when you heat, you basically cap this part. So you basically grow and then you cap by silicon dioxide again. And so you grow silicon dioxide and then you heat them. So heat it. So therefore the silicon will be, this part will be doped depending on kind of atoms that you had grown. So this is one of the way that you can grow, you can dope the silicon material. Now what happens, like you introduce the dopant atom, the silicon. Now when it diffuse, I have discussed about this earlier, that basically this atom has to move and replace some of the silicon atom, and so it has to diffuse on inside the material, and it come across some kind of energy barrier, and that normally called the activation energy, right, which you know. So this activation energy. So now what happens is that it can, you can have a already created vacancy where there is no atom. So this dopant atom can take place of a particular vacancy, or it can sit somewhere in between the. So now you remember that this position is not part of the crystal. So wherever you have empty space in the unit cell, it can sit. So that is sort of like interstitial position. It occupies the interstitial position. So this is the diffusion mechanisms that happens inside the solid. It can be quantified, right, by steady state equation. So this is called J. So J is the diffusion flux, right, and D is essentially diffusion constant, and C is the concentration of atoms uh, that you do, which is very important. So this is decided by this equation. J is equal to D into dc by dx. So the x is essentially the depth, right? So this is how actually the diffusion takes place, and the d, which I already said, that is the diffusion constant, which actually is an exponential function of ed, and this ed is activation energy of diffusion, which I discussed earlier as well in earlier classes. Now this, from these equations, one can derive a equation which looks like an wave equation, right? And this derivation I'm not going to put up here, but you can see in the book I refer in this topic for chapter 5. So once you have this, and then all you need to do is that this is a second order differential equation you solve, and if you solve it, then you get the Cx. So that's the concentration of the atoms that you deposit, and there are several parameters. But what is important is this X, how depth this atom that you deposit on top of the substrate, and allowed them to diffuse inside the material. So what is the depth they can go? So that is x, and which is essentially 2 into square root of d into d. Now it's important in this case because this depth depends on many parameters. Okay, so d1 in this case and d2, so there are two other parameters, which is d1 is the diffusion constant at pre-deposition temperature, and t1 is the pre-deposition time. So the pre-deposition temperature time, like when you deposit the film or the dopant film at some temperature, maybe room temperature, that's the T1, and then you anneal it to the T2, and then of course the T1 and D2 will be two different numbers, because when you heat it at high temperature, your diffusion constant is different than in the room temperature when you deposit the film. Fine. Now if you plot this, what you see here is basically Cxt by C naught. C naught is a constant, and this is what the x is. Now depending on this value, 1 micron, half micron, and 0.1 micron, you see the depth at which you can do. So this gives you some quantitative estimation regarding the depth of the doping. How depth, what is the typical depth that you want to do? For example, in case of let's say you want to drop like 2 micron, then of course you have to take the square root of dt is sort of like around 1 micron, and such that you have some kind of some doping concentration. So this is sort of like guideline, and of course so this is the diffusion under constant surface concentration, and when you pre-deposit, and of course their diffusion length is even less than that, less than depth. So essentially what it means is the annealing temperature, right? You have to decide a specific annealing temperature that gives you a specific diffusion constant, and you can sort of like estimate that what is the depth of the layers that you dope with the doping material, right? Now let's move. Once you dope, what happens to the atoms that are inside the crystal? So there are different kind of, they introduce defects. So you have defects in the crystals, and you introduce the defects also, and then these atoms which you dope, they you know uh, take part into a dynamics inside the crystal to form a stable structure. So it is all about interaction of dopants with the native point defects, because you have to have defects there. So now there are several kind of defects that you have, and this I think discussed in some point earlier. So you can have a vacancy, like you have a missing atom, right? And you can have interstitial impurity, as I said, that this is the dopant atom. It doesn't replace one of this position, but it sits somewhere in between. So that is called the interstitial impurity. Now this atom can sit there also, so then it is occupying a lattice point. Now you have self-interstitial. Now it can also happen. So this is also another kind of defect, that if a specific atom is not sitting in that right position, so this moved, and therefore some sort of defects it's created inside the crystal. So that's called self-interstitial, or you can also have substitutional. Right? This atom can sit right there. So these are different types of point defects that you can have, and of course when you do, then these defects take part for accommodating the impurity atoms. What are the mechanisms, diffusion mechanisms, when you introduce? Now let's say your doping atom sitting in the vacancy. Now it can happen, and that it can have some sort of exchange, direct exchange with other atom. So this silicon atom moves here, and this dopant atom moves there. So this is called the direct exchange, and that's how you can have doping. Substitutional diffusion. So let's say I have a defect, so I have an empty vacancy here, so this can directly go there. So that way also you can dope. There is another mechanism which is called the ring mechanism. Okay, what is ring mechanism? That a diffusion atom, a dopant atom is sitting in the in one of the space vacancy, and then sort of like a ring diffusion. So this moves there, this moves there, this moves there, this moves there. So that's why this doping atom can move either here, here, here. So it can occupy one of these three positions. So that is called the ring mechanism. You can have interstitial diffusion. So when it is sitting at the interstitial position, this also can diffuse to another and occupy another interstitial position. And there are several options for this, and it's called a kick out mechanism. And this can actually kick one of the silicon atoms and then sits there. It's also can also happen. You can also have Frankel Turnbull mechanisms where a vacancy catches at interstitial dopant position. So you have uh, you know dopant atom sitting at the interstitial position, but it can actually occupy one of these lattice state. So these are all different types of lattice diffusion that takes place inside the material after you dope the material, and that's very important. Okay. Now remember that depending on the dopant position, your electronic structure changes, because when you consider a specific materials with specific arrangement of the atoms, your potential is fixed. Now when you change it a little bit, then potential changes, and therefore your electronic structure changes. So it's very important to know that where these atoms, dopant atoms, are going, and what are the changes, crystallographic changes that takes place because of the dopant. Now, how do we do this? Doping can be achieved by a solid, liquid, or gaseous source. So your gaseous dopant source can be either solid, can be either liquid or gas, right? And you can use and there are several techniques I'll show you, but one of the things is the diffusion tube furnace. So you take a furnace and take a solid source, and so this is the furnace. So you take a solid source, right? So it's a tube, right? And so in this part you have a heater where you take the source, this is solid material, and you heat them, right? So for example, here you have P2O5 for deposition of phosphorus, right? And then you keep the substrate here. So this is another temperature zone. So it's a tube where you have different temperature gradient. So here you can heat, and you increase the temperature to, in this case for this material is 250. So when you increase this, then these molecules or atoms started sublimating. Now when it sublimates, then of course there is a gas which is nitrogen, flows through this, and it carries the atoms that you sublimated. And here you have a condensation region where you have lower temperature when you keep the surface, and then these atoms actually are deposited on this substrate that you have. So this is the tube furnace where you can deposit your dopant material. Fine. So this is a list of some of the materials that are used for doping a different material like phosphorus, boron, and these are all solid source, okay, in different form, and their respective temperature, group sublimation temperature also is given for reference. Now you can have liquid source as well, like boron tribromide. This is a liquid source, and you have different arrangement in this case. So this is the dopant that you need. Now you keep it inside a hot temperature bath, and then you heat them. These gas molecules are entered into the furnace and get deposited. Okay. Now there are gases, mostly like nitrogen is used, which is the gas to carry the dopant molecules. So it carry. You can also use oxygens to if you really need to do some sort of reaction. For example, in this case, this oxygen reacts with boron tribromide and then deposit B2O3, okay, boron trioxide. So this is what is just deposited here. It's sort of like CVD system that I discussed earlier. Excuse me. So now, so these are again the list of some liquid dopant materials which you can use to grow. Now you remember this temperature is low because this is in liquid form, so it's low temperature, the sublimate. So that's also so very good because at a very low temperature you can process. Now the gaseous phase, right? So there are many gas like arsine, right? Diboron, right? So to deposit arsenic and boron. So these are the different gases. Now this is simple because you have pure gases, so you basically transfer them into the furnace and let this uh, gas molecules do some sort of chemical reaction on the surface. Again, it's sort of like chemical vapor deposition, and then you deposit the film for the rope. Typically, nitrogen are used as a carrier gas, and oxygen is used to react with the dopant gas. Okay. This again the list, some of the showing some of the gas molecules which are normally used for doping, right? Like boron, phosphorus, arsenic. Fine. So this is these are the few techniques that are used for the deposition of a small thin film on a very specific area of the substrate, and then all you do is you anneal the substrate and allow these deposited atoms to diffuse inside the crystal and take part into the lattice, forming a lattice, specific form lattice.